going to go to pick up from here. So just as a review, we were able to use the periodic table to determine not only what layer the valence electrons are in, but how many valence electrons there are. So if I just pick a random one, say phosphorus, phosphorus has 5 electrons in the 3rd layer. That's what the valence is, right? And we went through these. So now what does that tell us? So what that tells us is what they're going to do when they react. So if you remember metals, but we haven't talked about that, but we will in a second. All right, the octet rule says that atoms, basically it says atoms react to be more stable, and more stable is a full or empty valence. Now why is that? Sometimes it's just because it's based on experiment, and every element that we found that has a full or empty valence is very, very stable. Oops, looks like my Zoom session is over. Sorry about that. Okay, that just popped up. All right, so now, so what they do, the reason it's called the octet, if you look, there's 8 columns except for that middle area. So the idea is a full valence and an empty valence are actually the same thing, because if you empty the valence, the one underneath it is filled. It's called the octet rule because we like to have 8 electrons. So typically what they do is they do whatever's easier. So metals like to lose electrons, non-metals like to gain. Just to show you using the whiteboard here, all right? If we go to the whiteboard, do I still have it up here? I did. There it is. Okay, if we go to the whiteboard, let's say we look at something like aluminum. All right, so aluminum, if you look at your periodic table, aluminum is in column 13. That means it has 3 electrons in the valence. That means it would have a choice. It could either lose all 3 and have 0, and that would do that by spitting out 3 electrons, or it could get to 8 electrons, but to do that, it would have to gain 5. And if you think of it like money, that for every electron you have to gain or lose, you have to pay $1, but if you get to here or to here, you get paid $4. So here you're paying $3 to get 4, here you're paying $5 to get 4. So what's it going to do? Well, it's not going to do this. It's going to do this. And if you lose electrons, you become positive, so this would be a 3+ charge. If you want to remember a joke to help you remember it, 2 atoms go walking down the street. One atom says to the other, you know, I think I lost an electron back there. First one says, are you sure? The second one says, yeah, I'm positive. So you can kind of use the periodic table to kind of figure that out. All right. So for example, if we look at something like sodium, sodium is in column 1. It's got 1 valence electron. So what's it going to do? It's going to lose 1 electron. Therefore, its charge will be +1. Again, this is where it'd be very handy to have a periodic table just sitting on your desk. Nitrogen is in column 15. That means it has 5 valence electrons. Now, it's either going to lose all 5 or it's going to gain 3 because we want to have 8. Well, what's it going to do? It's going to gain 3. Okay. Oxygen is in group 16, 6 valence, so we're trying to get to 8 or to 0. So either lose 6 or gain 2. Well, it's going to gain 2. Remember, electrons are negative. Chlorine is in group 17, so it's in, the same idea. Right? So here's some more. Try these on your own. Hit pause. Right? Did you try it? Let's see how you did. Okay, first thing you want to do is find it on the periodic table. Look at the column number, how many valence electrons, right? And just as where, like I said, it's a map. Barium is in column 2, sulfur is in 16, aluminum I did as an example, right? So it's going to have 2 valence electrons. It either wants to get to 8 or 0, so it's going to lose 2. Sulfur is in the same column as oxygen. It's going to gain 2. That one we did. All right, so see the idea? So there's some questions like this on the homework and even on the reading assignment. All right, now, some other things. We're almost done with these slides. One of the most important concepts in chemistry, because we have protons and electrons, we have charged particles. All right, and that means how charges behave is very, very important. Now, this is called Coulomb's law, and we're not in this class going to do the math, but this mathematical relationship explains how charges work, all right? And you actually knew this, you just didn't know it was called this. So let me tell you what these symbols are. F is the force between the charges, and a force is a push or a pull. K is a constant, who cares, it's a number. Q1 and Q2 are the charges, so it could be +1, -1. It could be +3, -2. It could be +2, +5. It could be -3, -6. Doesn't matter what the charges are. All right? And then R is the distance between them. So if you think mathematically, all right? First of all, one other thing. If the force is negative, so this is a plus and a minus, plus times minus is a negative number, how can you have a negative push or pull? In the sciences, we use negative to express direction. So if I say up is positive, then down is negative. If I say in is positive, then out is negative. If I say to the right is positive, then to the left would be negative. And if you remember when you learned about negative numbers, they used a number line. 1 and -1 are the same value, they're just different directions. So it turns out if the force is a negative number, it's called a force of attraction. And everyone says this, right? They go opposites attract. Typically they use that for relationships, which does not work. I've done the experiment. But opposite charges attract. If the force is positive, so they're both positive or they're both negative, right? A negative times a negative is a positive number. That is a repulsive force, they push away, right? So like I said, you knew this. If the charges are the same charges, alike charges repel, opposite charges attract. Now some detail, that's important. The bigger the charges, the stronger the interaction. And it doesn't matter if it's attractive or repulsive. What I mean is if this is a +1 -1, it's going to attract. If it's a +5 -5, it's going to attract even more. Okay? If this is a +1 +1, it's going to repel. If it's a +5 +5, it's going to repel more. So the bigger the charges, the stronger the interaction between them. And also the distance. As the distance, because it's in the denominator, as the distance becomes bigger, charges get further and further apart, the attraction between them decreases. And it decreases a lot because it's the distance squared. So if I double the distance, the force goes down by 1/4. If I triple the distance, the force goes down by 1/9. So it goes down very quickly. So size is very important in charge in the atom. And in the atom, why is this important? Let's think of it as the nucleus and the valence electron. All right, so let's look at what that means. So this is a little piece of the periodic table graphic. And this is the sizes. These numbers are in picometers, and it doesn't matter what those are for this class. All right. And remember, in the same row, the atoms are in the same layer. So all of these, the valence electrons are in the first layer. All of these, the valence electrons are in the second. All of these, of course my phone rings while I'm doing this. All of these, the valence electrons are in the 1, 2, 3, 4, 5th. All right? Now, as we go across the row, atoms get smaller. Why do they get smaller? Well, it's because as we go across the row, the nuclear charge, again looking at a periodic table, +3, +4, +5, +6, gets bigger. But since the electrons are basically in the same layer, that plus getting larger is pulling on the valence electron. It's going to pull it closer and closer and closer in. So across the row, atoms are going to get smaller. That means, going back, if the atoms get smaller, that means the attraction between the electron and the nucleus is going to get bigger. So as we go across the row, attraction for electrons should increase. So fluorine should have a stronger attraction for electrons than, say, boron. Right? And this is measurable. They found this by bouncing X-rays off of things. Down a column, the atoms are going to get larger. Now, why are they getting larger? It's because the valence is in a different layer. So there's one electron in the valence here, right? And it's in the first layer. But this has only one electron in the valence, but it's in the second layer, third layer, fourth layer, fifth layer. And so every layer is significantly further away. And look how big these blow up, 150, 180, 230, right? Really big. They get bigger way faster than they get smaller. Now, as the atoms get bigger, what is that going to do to the attraction for electrons? Going back 2 slides, right? This is going to get bigger. That means the attraction for electrons is going to get smaller. So as we go down a column, they have a lower attraction for electrons. So cesium would have much less of an attraction for electrons than, say, sodium. All right? So just to summarize it, attraction for electrons increases to the right and decreases down. So you would expect the highest attraction for electrons to be up here, right? Higher, they get lower this way. Now, why is that important? Well, let's see what the next slide is we're at a good stopping point. Just to sum this up, okay, then we'll stop and do the last video. As we go across a row, atoms get smaller, so attraction for electrons increases. Now, let's put it together. Nonmetals, we said if you really back it up, nonmetals like to gain electrons because nonmetals like to gain electrons. That means they're going to get more reactive, because nonmetals are trying to gain electrons, and as you get smaller and smaller, it's going to be easier to gain electrons. Nonmetals like to lose electrons. That means as we go across a row, the atoms are getting smaller, right? It's going to be harder and harder to lose electrons because smaller atoms, the electrons are closer to the nucleus. So you'd expect metals, as we go this way, to become less reactive, nonmetals to become more reactive. Going down a column, the atoms get bigger. So don't try to memorize this. You'll get yourself confused. So you could just think it through. As we go down a column, they get bigger. That part you should remember. That means it's going to be easier to lose electrons, and it's going to be harder to gain them, because the only thing that's pulling them in or keeping them in is the nucleus, which is increasingly distant. Metals like to lose electrons, so they're going to be more and more reactive. Nonmetals like to gain electrons, but they should be less reactive. So you would expect the most reactive metal to be here, and the most reactive nonmetal to be over here. All right? So try this on your own. I'm going to stop this video. Just for each metal, what's going to be more reactive? Okay? And I'm going to stop the video, and then we'll come back and finish this.